All right, guys, we are looking at our final chapter, final section of chapter 7, and chapter 7 is our final chapter. So this is our last new content of the year. Very exciting. I think it's a fun one too. We are solving exponential and logarithmic equations. It's really the pinnacle of chapter 7, which is on exponential and logarithmic equations in general. And now we're going to be solving them. And what I mean by solving, of course, is we are looking for the value of x that makes something a true statement. Now, something I've kind of avoided this entire time when we've been talking about logs is kind of getting down to the purpose of them. Why are they used? We've done different things with them. We've converted from exponential to logarithmic form. We have used the product properties and the quotient properties and those things to condense and expand. And we've also done the change of base formula. And a lot of that same stuff that's in those things that I just talked about are still going to be used in this section. But we also need to introduce something that is very key and new. And that is, let's say I have 2 to the x power is equal to 10. Okay, 2 to some power is 10. We could approximate this. We know that 2 to the third is 8. So it's going to be a little bit more than 3. Now, the whole purpose behind logs and logarithmic equations is that we want to be able to get x out of our exponent. We want to be able to solve equations where x is up there. And up until this point, we don't really have any skills that would do that for us. Now, this I'm going to refer as 2 to the power of, right? 2 to the. The key to this is that 2 to a power and log base 2 are inverses of each other. So 2 to some power, okay, doesn't really matter, and log base 2 are inverses of each other. Remember, addition, subtraction are inverses of each other. Multiplication, division are inverses of each other. 2 to the power and log base 2 are inverses of each other. They undo each other. Similarly, 3 to a power, log base 3. 10 to a power, log base 10, right? E to a power, log base e, or the natural log. Those things are all inverses of each other. They undo each other. So let's look at this example. We have 2 to the power of x is equal to 10. Well, what undoes 2 to a power? That would be log base 2. Now, we've made it this far in Algebra 2. We know that if we do log base 2 on one side, we're going to have to do that same thing on the other side, right? Otherwise, we've made the equation no longer balanced, no longer the same. So if I do log base 2 on that side, I also have to do log base 2 on this side. So I'm going to rewrite this. What it would look like would be log base 2 of 2 to the x is equal to log base 2 of 10. We took our original equation, 2 to the power of x is equal to 10, and we did log base 2 on both sides. Now, I told you guys that log base 2 and 2 to the power are inverses of each other. They undo each other. It's kind of like doing plus 2 and minus 2. They cancel each other out. So those cancel, and when they cancel, whatever's the exponent actually is just going to become full size. So log base 2 of 2 to the x is just actually x, because log base 2 and 2 to the power cancel each other out. Now, this side, they don't cancel each other out because they're different bases, right? We have base 10, and then we have, or base 2, and then we have 10. So x is equal to whatever log base 2 of 10 is. And we know the change of base formula to do this, right? The change of base formula says, back up. We can't really do log base 2 on our calculators. So what we do instead is we use the change of base formula, which allows us to use the log button, because we can pick any base that we want to with the change of base formula. So we're going to pick base 10. Remember, we don't write the number 10 down here. So what it looks like is you take log of the full size number 10 and divide that by log of the base 2. I'm going to go into my calculator and I'm going to type that in. Log 10, close parentheses, equals, and then I'm going to divide that by log 2, and I get 3.32. 3.322. We like to use 3 decimal places. So we could verify this. We could say, hey, when I plug 2 back in, 2 to the 3.322, do I get 10? 2 to the 3.322, and I get 10.00049, which is fantastic. Okay, we are rounding here. That's why it's a little bit off. So that's one of the key ideas that we need to know as we proceed in 7.6, that 2 to a power and log base 2 are inverses of each other. We need to expand this though. 3 to a power and log base 3 are inverses of each other, right? We can keep going any set of numbers as long as the base of the exponent and the base of the log match. These ones are actually easier than the last thing. We have 10 to a power. Well, what undoes 10 to a power? Log base 10. Well, we don't write log base 10 because if it's no number there, we know it's 10. If I do it to one side, though, I have to do it to the other side. I can actually do log base 10 of 108 by typing in log 108, and that is 2.033. Log base 10 and 10 to the cancel each other out. The exponent becomes full size. X is equal to 2.033. This one here is really similar. I hope that you guys are thinking, hey, what undoes e to a power? Well, that would be log base e. Log base e, of course, is the natural log at the ln button on your calculator. If you do it to one side, you also have to do it to the other side. And I can figure out what ln of 351 is. It's 5.861, or about 5.861. ln of e to the power cancel each other out, right? That's log base e of e to a power cancels out, and so we get the exponent becoming full size. 5x minus 1 equals 5.861. Now I have a very simple algebra equation I can solve. I would add 1 to each side and get 5x is equal to 6.861, and then divide both sides by 5 equals 1.372. Should be very easy to check this. Plug it in for x. I have an e my calculator to the power of 5 times 1.372 minus 1. I get 350.7. Okay, once again, we are rounding our decimals, so we are going to be off a little bit. In this problem, we're off by 0.3. Okay, it's just going to be part of the deal, but that is our solution. I'm going to skip both of these. I think you guys get these. This one, we would do log base 3, right, because that undoes 3 to the power. If I do it to one side, I would have to do it to the other. I guess I'm doing this anyway. Log base 3 of 3 to the power is x. Log base 3 of 150, this we have to use the change of base formula, which would be log of 150 divided by log of 3. I type that into my calculator. I get x is about 4.561. A lot of times you're going to see that about equal to equations instead of just the straight lines. These questions are a bit trickier. I'm not going to assign a whole ton of them. You might see one of these on the test. You look at these and you're like, well, they don't have the same base currently. Yeah, see that? Same with 100 and 1,000. In these types of scenarios, though, I'm always going to make it so that the numbers could be written with the same base. 9 and 27, I hope at this point you guys look at those and you say, well, 9 and 27 do have something really in common. 9 is 3 to the second power. So I replaced the 9 with 3 to the second power, and 27 is 3 to the third power. Now, we have a property of exponents that says if you have something being taken to a power, being taken to another power, you would multiply the exponents and get 3 to the 4x power. So I'm taking those exponents and I'm multiplying them. I'm going to do the same thing here. This one would be 3 to the 3x minus 3, because when I multiply 3 times x minus 1, I'd have to distribute. Now, both of them are 3 to the power. This is going to be really actually pretty nice. We know what undoes 3 to a power. That would be log base 3. If I do it on one side, I would also have to do it on the other side. So I'd have log base 3 of 3 to the 4x is equal to log base 3 of 3 to the 3x minus 3. Well, log base 3 of 3 to a power cancels 4x. Same thing here, log base 3 of 3 to a power cancels. Now I'd have 3x minus 3. Now I don't have any exponents. This is actually a fairly simple problem to solve. I would subtract 3x on both sides. Now I'd get x is equal to negative 3. Ta-da! Very exciting. We can do the same thing here. 100 and 1000 could be written with the same base. I hope you see that as 10 squared and 10 cubed. So this would be 10 squared to the 7x plus 1. This would be 10 cubed to the 3x minus 2. Same idea. If you have something being taken to a power being taken to another power, you multiply those exponents. This would be 10 to the 14x plus 2 is equal to 10 to the 9x minus 6. Same idea. What undoes 10 to a power? Hopefully you are audibly just being like, yes, log base 10 undoes 10 to a power, right? Those are inverses of each other. Log base 10, we don't really ever write log base 10. If there's no number there, we know it's base 10. But I wrote it just to be clear. Those cancel. We get 14x plus 2 is equal to, those cancel. 9, no. 9x minus 6. Subtract it over, we have 5x. Subtract the 2 over equals negative 8. So x is equal to negative 1.6. I'm going to close this part A of the video before we start solving logarithmic equations. All of the ones that we just did were exponential equations, where we have exponents and we're trying to solve for x in our exponents. We're also going to look at logarithmic equations, but these are pretty good ones to try if you wanted to. I'll just show you what the bases are. This one, both 8 and 32 could be written as 2 to a power, right? 2 to the third, that's supposed to be a 2. Takes in 2 to the 5th. So this would be to the x plus 2. And this would be 2 to the 5th to the 2x. And both of these could be written with the base of 5. So, like I said, I'm going to end it here. Hopefully, solving the exponential equations makes sense, and we'll look at solving logarithmic equations in the next lecture.